Yo,
Yo, Arlie, how are you?
good. I have my lecture tomorrow, but
Oh, you have the lecture tomorrow? Let's see, that's good. What time?
at like 9 a.m.
9 a.m. Okay, okay.
Yeah, but I guess is it okay if you I don't know, teach me before I go to first lecture? I think the first thing we're learning is like the conjugated diene stuff.
Yeah, conjugated diene stuff like
Yeah,
deals all their kinetic
yeah.
thermodynamic reactions. Yeah,
I think
I
the first
could
one is the thermodynamic versus kinetic stuff. So
yeah, thermodynamic kinetic stuff. Let me try teaching you that. Let
just
me
like a
see.
quick rundown of it
Yeah, a quick rundown.
stuff.
Let me see here. Let me make sure. Give you the right stuff. Okay, chapter. Yeah, here.
But yeah, my OChem lecture is gonna be 80 minutes instead of 50 minutes.
Oh, 80 minutes, so now it's
Yeah,
20 minutes. Let's see, that's
yeah.
good.
So
Tuesdays
it's
and
not like,
Thursday.
yeah.
Yeah, that's good.
So it shouldn't be like I shouldn't get bombarded with like new topics
Uh-huh.
every Monday, Wednesday, Friday. That's so bad.
Yeah. 3 times a week. Oh my
Yeah.
gosh. Yeah. Okay, so um conjugated diene is going to be when we have two alkenes that are conjugated with each other. So a simple example would be something like this, where we have these two alkenes, one, two,
Yeah.
that can do conjugation with each other, do resonance with each other like that, right? I'm going to add, let's say, this methyl group on the second carbon like this, and let's say we react this with HX, where it could be like HCl, HBr, or HI, right? I'm
Mhm.
gonna use HBr right here. Um, we have two alkenes that can react with this HX. Let's look at the left alkene right here. So we have to figure out which carbon would give us our most stable carbocation, right? Like, would it be the
The one on the right.
Yep, the one on the right. So that means that the one on the left is going to grab the hydrogen, kick out the bromine, in order for us to have the carbocation on the right,
Mhm.
right? And we see that this carbocation right here is a tertiary allylic carbocation. It's allylic because it's on the
One
allylic
away.
carbon, one away from the alkene.
Yeah.
Yes, right. And I'm gonna draw out the resonance structure of this by shifting the double bond over there, which is going to give me this carbocation right there. So that's the resonance set using the left alkene right there, right?
Hmm.
Now that was if we reacted with this left alkene. Let's do the same with the right alkene. Um, we see that the more stable carbocation is on the left carbon, right? Because it's more substituted and it's also allylic, right? Like this carbocation here at this carbon would be more
Yeah,
stable
yeah.
than the
Mhm.
carbocation over here, because this carbon over here is more substituted and it's allylic as well. So that means this carbon here is gonna get protonated, kick that out to give me this carbocation right here, right? Now once I have this, I could shift this double bond over here to give me this resonance structure right here. Okay. Now, once I have my two resonance structures, I have to choose my best resonance set that has my most stable carbocations, right? And to do that, we could label each one. This is tertiary allylic. This is primary allylic. This is secondary allylic. And this is primary allylic. We see that the top resonance set is better than the bottom resonance set because of this tertiary allylic carbocation right here, right?
Mhm.
So we can basically ignore this bottom set right here,
Okay.
um, right? Because I'm gonna show you what the difference between thermodynamic product is and kinetic product is now. Uh, Kinetic product,
I have a question.
yeah, uh-huh.
Will it always be allylic? Like when you're doing conjugated dienes, or is this just like a
Mm-hmm.
usual thing?
Yeah, it will, like when you form the carbocation, we will. more likely form the allylic carbocation because it is more stable, right? Because if I were to give you this conjugated system right here, and I react it with HCl, and let's focus on this alkene right here. Which carbocation do you think is going to be more stable? Do you think that it would be more stable at carbon A or carbon B? The carbocation.
B.
B. It looks more stable because it looks more substituted, right? But
Yeah.
if I put the carbocation right there, can this carbocation do resonance?
No.
No. So this is not allylic, right? The more stable carbocation would actually be A, because it, even though it's less substituted, it is allylic. It's able to do resonance with the alkene like that, right? And this resonance factor here makes this secondary carbocation more stable than this tertiary carbocation, because this is not only secondary carbocation, this is a secondary allylic carbocation, which makes it more stable than a regular tertiary carbocation.
Okay.
Right.
So
that's
there's always preference for the allylic versus any like tertiary, just without the allylic.
Yeah, right, because the allylic allows for resonance, which is a stabilizing factor. Yeah.
Okay. Cool.
Yep. Okay. Nice. So now the kinetic product is going to come from the most stable intermediate. Right? And this intermediate here can be different things from different reactions, but the reaction that we're talking about now is a carbocation intermediate. Right? So that's what the kinetic product is going to come from. The thermodynamic product is going to make the more stable product, like overall product. Thermodynamic product is going to make the most stable product. And in this reaction, the product that we're going to look at is the alkene, the more stable alkene. Right?
Okay.
So we know that we're going to ignore the bottom set because that's the worst one. And we're going to look at the top one right here. Right? The purple is how we labeled our carbocation, the intermediate. The green is going to be how we label our alkene. Right? How would you categorize this alkene? Is it unsubstituted, mono-substituted, di-substituted, tri? Mono, yes. Mono-substituted because there's only one group coming out of it. What about this alkene right here? Tri, yes. Right. Now, this is going to be professor-based now. The way you tell whether you're going to go for the kinetic product or your thermodynamic product is going to be temperature-based. Kinetic product is going to come from low temperature.
Okay.
Thermodynamic product is going to come from high temperature. Heat. Right? High temperature. Heat. So Levens is teaching 128C this quarter, so she will most likely give you the temperature for...
Yeah, I think though, like she posted like some practice like conjugated diene, and it says like she uses -78 degrees Celsius for the cold one.
Yes.
And then 40 for the hot.
Right. So for Levens, -78 degrees Celsius for the kinetic product, the cold one. The hot one, the thermodynamic one, she will use 40 degrees Celsius. Okay. So let's say that we are gonna draw the kinetic product in pink and the thermodynamic product in blue. Now we have two intermediates to choose from. Let's say this is intermediate A and intermediate B. Let's draw the kinetic product first, the one in pink. Would it come from intermediate A or would it come from intermediate B?
It's A because it's the more stable intermediate, right?
Yeah, right. And that's where the like kinetic product comes from, the more stable intermediate. So the Br minus that got kicked out earlier in the first step will attack that carbocation, leading to the kinetic product. The thermodynamic product is gonna look for the more stable alkene in this reaction, which is coming from this intermediate here because this is the tri-substituted alkene. So the Br minus is going to attack that carbocation, leading to the thermodynamic product like that. Right. And this is bromine right here. Okay. Yes. And depending on the temperature, you're only going to be drawing one of these. Like you won't be drawing two of these. Right. Depending on what temperature you're given. Right.
Wait, so if you're not given a temperature, you would have to draw both, right?
If you're not given a temperature, you're gonna assume kinetic at least for helix, right? If you're not given a temperature. But I don't know about for leave-ins. Yeah, I'm not sure. Yeah. Right. Okay, so that was the reaction with HX. I'm gonna give you a practice problem to try it out on, and I'm gonna show you the reaction with X2 afterward. It's the same like process, but different mechanism at the beginning. Okay. So let me give you this here. Okay. Okay. And let's say this is HCl. Draw both the kinetic product at negative 78 degrees Celsius and thermodynamic product at 40 degrees Celsius. Right. Okay. For this one here. Okay. Hey, Suparna. Oh my gosh, long time. No see. Like, so it's been like 9 months, like since last summer.
Yeah, it's been a really long time.
Yeah. Oh my gosh. What year are you now? Are you third
junior.
year? Junior year.
Yes.
Yes. Okay. I see. Did you have your lecture yet for helix?
Yes.
That's good. What did you guys go over so far, or what did you want to go over today?
I was wondering if you could just do like a review from 118B because I don't remember much. And then I think we just went over carboxylic like nomenclature, like formic acid, acetic acid. He talked a little bit about just like IR. We didn't do much. His projectors were kind of down today. So we only spent like 30 minutes on class. So
30 minutes in class, I say, yeah. And I say the review slide from Chem 118B, what he wants you to know. Which is gonna be this.
I don't remember all of that.
Right. The first one I see here is nucleophilic addition into a carbonyl. Right, and there's two subcategories of that, which is gonna be organometallic and hydride reagents. And then the other one is going to be various other nucleophiles. And that would lead into the other ones that you see, hemiacetal, acetal, amine reactions with carbonyls. Right, those are the various other nucleophiles. So instead of this going over the various other nucleophiles, let's just talk about the organometallic and hydride reagents one first. Right, so a carbonyl is like an umbrella term, right? It's a carbon double bond oxygen. That is a carbonyl. And there are many carbonyl functional groups in organic chemistry. There's like the aldehyde, the ketone, ester, amide, carboxylic acid, and hydride. Like there's a lot of carbonyls. Right. So I'm gonna separate the two carbonyls, like families, into this right here. I'm gonna separate it into the aldehyde and ketone. Aldehyde slash ketone. Aldehyde slash ketone. And everything else that you need to know for 118C is going to be carboxylic acid, acyl halide, anhydride, ester, and amide. Do you remember what these functional groups look like, Suparna?
Yeah, I think it's coming back to me. But...
Yeah. So like an aldehyde, right, would be like when we have a carbonyl that is going to be in the middle of R and H, right? It has to have that H there. Like a hydrogen is hiding in that molecule, right? A ketone, you can think of it as like a carbonyl in between the two different R groups. An R group here is just like a hydrocarbon chain, like anything with a carbon and hydrogen, like methyl, ethyl, isopropyl, tert-butyl, something like that, right? A carboxylic acid is going to be when we have a carbonyl that is in between an R group and an OH group, hydroxyl group. Acyl halide is going to be when we have carbonyl in between an R group and an X group. An X group is a halogen, right? Where it could be chlorine or bromine. It could be iodine as well, but then the two most common ones you see for this unit is chlorine or bromine for this acyl halide, right? So it could be acyl chloride if the X is chlorine, or it could be acyl bromide if the X is bromine, right? Now, anhydride is going to be this funny looking structure right here, where this is the carbonyl we're interested in, and it's attached to an R group and this carboxylate group right there, right? It's like another carboxylic acid, but it doesn't have that H. Like it's like the exact carbon copy of another carboxylic acid, except this H right there, right? An ester is gonna be when we have a carbonyl in between an R group and an OR group, right? I'm putting primes here to show that these R groups do not have to be the same, right? They can be the same for some examples, but most likely they won't be the same. So that's why I'm putting a prime right there. Amide is going to be when we have a carbonyl in between an R group and an amine group, right? And there's three types of amides that we could have. We could have that amide. We can have this amide. Or we can have this amide, right? But depending on what kind of amine we have, like what kind of groups are attached to that nitrogen of that amide right there. And the nitrogen wants 3 bonds to be neutral, right? Like in all 3 amides, the nitrogen atom here has 3 bonds. Okay. All right. So the biggest difference between these two categories of carbonyls is the one on the left has no leaving group. And I want to abbreviate leaving group as LG, no LG. The one on the right has a leaving group, LG. And I'm going to circle that leaving group in red. Which is like that, right? All of these groups here, they are going to be relatively stable when they leave with a pair of electrons, right? If the oxygen leaves here with a pair of electrons, it will become negatively charged. It's stable because that oxygen is electronegative enough to handle that negative charge. This halogen here is stable with a negative charge because it's one of the most electronegative atoms on the periodic table. This carboxylate here, when it leaves, that negative charge right there is stable because this negative charge here can do resonance with the carbonyl here, right? With these arrows like that. We can move the negative charge down to create a double bond there, shifting this double bond over to create a negative charge on the oxygen, and that makes it stable. Okay, same as for the other leaving groups here. Like these are electronegative atoms that can handle negative charge. Whereas if you look at these ones here and you try to kick it out and give it a negative charge, these are terrible leaving groups, right? These are very bad leaving groups. Because they cannot handle that negative charge very well. This hydrogen here is not very electronegative, so it can't handle this negative charge. And it's also a very small atom, so the negative charge has no like space to roam around in. This R group here, like a carbon atom, right, is not very electronegative, so the negative charge here is not as stable on that carbon atom as well, right? So that's why we consider these as terrible leaving groups, and these ones here as good leaving groups. Okay. Any questions so far, Suparna?
No. I think it's all coming back to me.
Yeah, that's good. That's good. Like this is like from 1 to A, like just identifying the functional groups, right? Like the things of the structure, but be sure to know the difference between like an ester and an ether, an amide and an amine.
Yeah, I low-key forgot the groups.
Right. Do you remember the difference between these two? Here, like let's say ester and ether.
I'm pretty sure S ether doesn't have a double bond, I think.
Yeah. Ether does not have a double bond. It's just like an oxygen in between two R groups like that. Right. Same for the amine. The amine does not have the double bond. It's just a nitrogen that has three bonds, either to a hydrogen or an R group. Right. Okay. So when I go over this next thing here, actually, like this is actually gonna like especially with these ones here, this is the unit 1 material, the carboxylic acid, azo halide, and hydride ester amide. Like that's the midterm 1 material right there for 118C, right? But you did learn about what aldehydes and ketones from 118A, right? So he wants you to know that. And for this review, I'm just gonna go over aldehyde and ketone reactions for review. Right.
Okay, perfect.
Right. But then when we all go finish the review, then we'll hop into these ones here, the functional groups here.
Okay.
Right. Yeah. So let's talk about organometallic reagents. Organometallic reagents. So there's two types. There's Grignard reagent. And there's organolithium. Well, there's another one as well. There's the organocuprate one, the Gilman one, but that is 118B, and it probably won't come back in 118C, so you don't have to worry about that.
Love that.
Yeah, that's good. That's good. Less things to remember, right? You just know the stuff that you need to know for the new material, like from the previous quarters. 118A, you definitely need to know SN2, SN1, E1, E2 for sure. That's always gonna be there. Acid base reactions, like what's an acid, what's a base. Resonance, that's a big one. Steric hindrance, that's another big one for 118A. Nomenclature, how are your nomenclature skills? Like you think you can pick it up when you like do practice, like nomenclature, like naming molecules?
Sure. Wow.
Yeah, it's been a while. I know. Synthesis is another one, but the mechanism, like that's the no part thing.
I can't wait for that.
Yeah. We'll do practice. Don't worry. There's strategies behind that. The strategies, and you can pick up on patterns too. Okay, so Grignard reagent is gonna be like an R MGBR, right? Where the R group that is directly attached to the Mg is negatively charged. So an example would be something like this. If we have this structure here, the carbon directly attached to the Mg, magnesium, is negatively charged. So that's my partial negative charge carbon right there. That is my nucleophile or base, right? It could act as a nucleophile or base. Let me just write that down because that's very important. Strong nucleophile or base. If it has a chance to act as a base, it's going to act as a base first over a nucleophile, because acid base reactions are very fast, right? They're one of the fastest reactions that you can have. Okay, so an organolithium, it's like the exact same thing as Grignard reagent, but instead of RMGBR, we have RLI, right? So if we have something like this, the carbon directly attached to the Li, lithium, is the nucleophile, the negative charge, the strong base or strong nucleophile, right? Strong nucleophile, strong base. Okay, let's look at an example problem. Let's say we have this aldehyde, and we react it with this Grignard reagent as the first step. Second step, acid workup with H3O+. Okay. So there's two important concepts that you need to know before you do this reaction. The differences between a nucleophile and an electrophile. A nucleophile is going to be something that's negatively charged. An electrophile is going to be something that's positively charged. Right? In organic chemistry, the negative charge always attacks the positive charge. Never the other way around. So don't draw an arrow from a positive charge to a negative charge, because that's wrong, right? Always draw an arrow from a negative charge attacking something positive. Right? So a nucleophile will always attack an electrophile. Looking at the green reagent here, this carbon that is directly attached to the magnesium is my nucleophile because it's partial negatively charged. So I'm going to star that to identify my nucleophile. Looking at this reactant molecule here, can you identify any atom that is, let's say, partial positive charge? Looking at this molecule here, like any atom that is partial positively charged?
You're gonna have to tell me. Is it the carbon?
Yes, the carbon of the carbonyl. This one, yes, it is.
Yeah.
Right? Because oxygen is more electronegative than carbon, so that means oxygen is gonna withdraw electrons or pull electrons away from that carbon, making that carbon more positively charged. Right? So I'm gonna dot that carbon right there to identify that as the electrophile right there. Yeah, you got it. Right? Now, once we identified our nucleophile atom and our electrophile atom, we're gonna do the reaction. This nucleophile here, the star, is gonna attack the electrophile, the dot, like that. When that happens, we're gonna make a new bond, right? We're gonna make a new bond between the nucleophile atom and the electrophile atom. We're making a new bond between the star and dot right there. But there's a problem, right? Because
we have to push up the O.
Yes, we have to push up the O. Yes, you got it. Right? Because that's gonna conserve the octet row. If we don't do that, this carbon here is gonna break the octet row. Right? Like it's gonna have 5 bonds. That's not good. So that's why we gotta push up the O like that. The MGBR here dissolves away in the solution. So when we connect the two molecules here, we're gonna make a new bond between the star and the dot. This is the new bond right here that we created between them. That new bond came from the attack. This dot here no longer is a double bonded to the O, but it's now a single bond O minus. The star here, right, has 2 methyl groups attached to it, which is this and that right there, like that. Okay, the MGBR dissolves into ions, into magnesium ions and bromide ions. Now, that's the end of the first step. What do you think the second step is going to do when we bring in the acid workup to lead us to our final answer? What is this H3O plus going to do with this O minus here? What is this O minus going to do with this H3O plus? It's
gonna take the H.
It's going to take the H, and the bond between the H being grabbed and oxygen is gonna break and go onto the oxygen like that to become water, right? So we're gonna neutralize the O minus to OH, and if you want to draw out the water as the conjugate base, you can for mechanism, but that's the final product right there. Right, where the big thing about organometallic reagents is that we are creating a new carbon-carbon bond, and the new carbon-carbon bond is this right here, right? And this alcohol here came from that carbonyl right there. So that's a good thing to know for synthesis, right? Because if you see a new carbon-carbon bond, you can think of organometallic reagents, like either Grignard reagent or organolithium reagent. And if you see an alcohol, then you could most likely say that that alcohol came from a carbonyl, carbon number 1 oxygen like that. Okay. Any questions on that reaction?
No.
Okay. I'm going to give you a practice problem on this organometallic reaction, and then I'm going to go back to Wiley and check his work for the kinetic thermodynamic product.
Yeah, I sent you on Discord.
In Discord? Okay. Let's see. Okay. Try this one out, Suparna, and then I'll go back and check, and then we'll move on to reduction, hydride reagents, for the next part of
Perfect.
the review. Okay, let me check. What is thing? Let's see. Okay. Oh. Okay, okay. Ignore that. And look at this one. Okay, yep. And then for the kinetic one, yep. Oh. Thermal. Okay. Yeah, I see that you got the two resonance structures correct, but how did you get to the kinetic product and thermodynamic product? Like, what did you do to?
Oh, I
What was
just
the thought
added
process?
the CL on the more sub.
Mhm.
Yeah.
For kinetic product, we want it to come from the most stable intermediate, right?
Yeah.
But well, I see your two resonance sets. Which set did you end up choosing to look at? The left one or the right one?
I chose the right one.
Yep, the right one, right. So we're gonna ignore the first one. Now looking at the right one right here. Which intermediate is more stable? The secondary allylic carbocation or the tertiary allylic carbocation?
Wait, it should be the tertiary one.
Yes, it should be the tertiary allylic carbocation. Right.
Wait, did I not draw it? Tertiary one?
So the tertiary allylic carbocation is this one, right? Like you're looking at this one, right? For the tertiary allylic carbocation.
Yeah.
Right. Yeah. And if we're looking for the kinetic product, the Cl minus is gonna attack that carbocation and give us this answer right here. Right. And you labeled that as the thermodynamic product.
Oh, did I?
Right. Because you circled or boxed the 40 degree.
Oh, I mixed it up.
Yeah.
Never mind. Wait, so oh yeah, I guess that makes sense. Yeah, I was kind of like unsure.
Yeah, let me
I should have like labeled it better.
Yeah.
Because I also put the colors.
The colors, yeah. I see.
But like the products themselves, like the molecules are right?
The thermodynamic one, if you look at the right resonance set, it should be this intermediate right here. Right, because this is the more stable product, more stable alkene.
Oh. Wait, did I not draw that? Okay, I see.
Wait, which will lead us to this product right here for 40 degrees Celsius product. This is the negative 78 degrees Celsius product. And the way that you labeled thermodynamic and kinetic product, right? I think it looks like you labeled the whole set as thermodynamic on the left and the whole set on the right as kinetic, right?
Oh, you can't do that? It has to be
you can't do that. Yeah.
Oh, okay.
Yeah, you're gonna completely ignore one set. We're completely ignoring the left one, right? Because the left one has a secondary allylic, while the right one has secondary allylic and tertiary allylic. So we're completely ignoring.
So it'd be better just to label all the resonance and then choose which one's more sub and which one's more stable intermediate.
Right.
Okay.
Like choose the molecule.
Can you draw the resonance for the very bottom one on your screen?
The very bottom one, the resonance for this one?
Yeah.
Yeah, these are resonance structures of each other. So these that's the resonance set on the right that you drew out.
Oh.
Right.
Oh, okay, that makes sense.
This is the tertiary allylic carbocation. This is the secondary allylic carbocation.
Oh, so you eliminate. Okay, so that's why the other two don't work. The one that I wrote on the left.
Right, the other two would completely ignore
you would choose between the left and the right one on what I. Okay.
Yes, yes.
Oh, okay, that
On
makes
the
sense.
resonance structure, yes.
So the thermo and kinetic are just only going to be based on one set of resonance structures usually.
Yes. Yeah.
Oh, okay, okay.
Yeah, one set of resonance structures. Not you're not
It's not like okay.
you. Yeah.
Okay, that makes sense.
Right. It's good. Yeah, it's a lot. Like the reactions here like require a lot of like process, you know. So if I were
Is
to
there like a quicker way to doing it, like recognizing which one, like without drawing all the resonance structures?
yeah,
Or do you have to like draw them
I looked for the quicker way to do it, but then like it could get tricky, you know. Like if you try to look for a shortcut, like you could mess up. Like you,
all? Oh,
you
okay.
get it wrong. So I would think about it, like which one would give you the most stable resonance set first, and then draw that out, and then go from there, right?
Okay. Uh-huh.
If I were to make a step-by-step like process on this reaction, the very first thing I would do is to like either visually or on paper, when you're first doing this and practicing with this, do it on paper, right? React both alkenes to get two resonance sets. Right. Then we choose the more stable resonance set. Right. More stable, like intermediate, more stable intermediate. More stable intermediate resonance set. Right. And then once you choose that, right, completely ignore the other one.
Okay.
Ignore the other one. Don't worry about that. Other set. Okay. Then you want to label the kinetic intermediate and your thermodynamic intermediate. Right, and for these ones that we've been working with, I'm gonna keep it general. The kinetic intermediate is the more stable intermediate, right? Like carbocation or radical, right? And then the thermodynamic intermediate is the more stable product, like alkene.
Okay.
Stable product. Okay. And then from there, predict the product based on the temperature.
Okay. And will it always be two resonance like sets no matter like how many alkenes there are in a conjugated system?
Oh,
or
if
could
the
there
conjugated
be like
system is bigger, then you're gonna get more resonance sets.
okay.
Right.
Yeah.
So that is like a possible question, but I think most of our practices with these are two alkenes, right, for the conjugated system.
Yeah.
Yeah. Right. Based on the temperature. Right, because if you were to have like this conjugated system with 3 alkenes instead of 2, to get the resonance sets, you would have to react like every single alkene, 3 alkenes to get 3 resonance sets, right? This will give you 1 resonance set, this will give you another resonance set, and that will give you another resonance set right there, right? But that is too tedious, so I don't think you'll be tested on that.
Okay.
But yeah. Okay. So that was with HX, right? You could react the alkene with X2.
Wait, can you scroll up? I need to screenshot the steps.
Right.
Okay, we're good.
It's good. Okay. Now I'm gonna show you the one with X2 instead of HX. So let's say we have something like this, and we react this with Br2. Yeah. Br2 and negative 78 degrees Celsius for kinetic, 40 degrees Celsius for thermodynamic. I'm going to look at this alkene right here. If I were to draw out the mechanism, right? I don't recommend doing this, but if this is a predicted product, I'm going to show you what to do after, but just to show you the mechanism. If we look at that alkene right there, we're going to form a bromonium ion ring, which is like that, like an epoxide-like structure.
Yeah.
Right? And usually, you know how the thing that got kicked out, Br minus, if there's no...
It's the nucleophile.
Yeah, it's a nucleophile, right? Attacks. In this case, we don't do that, right? Because there is a very good leaving group that it's just going to leave by itself, right? Like, we're just going to break that bond away because this carbocation here is extremely stable. So it's allylic.
Oh, yeah.
You could do resonance with the alkene right there. So that's the difference in this reaction. That's just going to leave by itself to form that allylic carbocation that is going to do resonance. Like this. Okay. Oh, wait. No. These are not resonance structures of each other. That's the next step. Okay.
Should be the arrow, yeah.
Yeah. Now we make the resonance set from here. There we go. Like that. Okay. Okay. Now, instead of drawing this out like that, looking at the other alkene, we know that this is the carbon that is more stable than this carbon. Even though this carbon here is less substituted, it's more stable because it's allylic. It could do resonance with this alkene right there.
Oh, yeah. Okay.
Right. So I'm just going to draw the carbocation right there, right away. Because that's the more stable carbocation. That means that the bromine is on this other carbon right there. Eventually. Right. And then that's going to give us this resonance set right here. And there's a caveat here that I have to update the step-by-step procedure on. But this is for more of a helix thing, because like this is very iffy with like the professors how they teach it, because like if you check the AATC worksheets, Maria Jones, she also says like for helix this is the answer, for Levens this is the answer, for Nisiri this is the answer.
Okay.
So I have to see her notes and see like how she teaches this with the exceptions and caveats. But I'm just gonna show the caveat here, right? Based on helix, because I haven't seen Levens teach 128C yet.
Okay.
Right? Okay, so now does this make sense so far on how we got to two resonance sets?
Yeah. Oh wait, could you like label the
yeah.
If it's tertiary, tertiary,
tertiary, allylic, secondary, allylic, secondary, allylic. Right? We're gonna completely ignore the bottom one because the top one is a better resonance set. Right? So don't even look at this at all.
Okay.
Okay. Now let's label the alkene. This is tri-substituted. This is also tri-substituted. Right. Now, if we're looking for the thermodynamic product, right? That means we're looking for the more stable alkene. They're both tri-substituted. So the thermodynamic product, we get two products here. This one. And
wait, is this wait, you said thermo, right?
Yeah, thermo.
Okay.
Right. The more stable alkene. They're both equally stable, so we get two products because there's no more equal stable alkene, right? Now the kinetic product, this is where the caveat happens, right? You know how they're both equally substituted and they're like both allylic? Some professors say like these two will be your kinetic product, but what Helix says, and I think what the textbook also says, is that, or for 118, I don't know what 28, is that even though they're both equal, this is the first thing that gets formed. So this is our only kinetic product here because it takes time to
Oh.
get to this resonance structure here, because like it takes time for that alkene to move over to form that product right there, right? And kinetic product, we want the fastest product formed, the fastest thing formed, right? And this is the fastest thing that gets formed right there, right? So we're only gonna get one kinetic product, even though the two intermediates are equally stable. We're gonna choose the one that gets formed first, the fastest one that gets formed first, which is that right there. And it should be bromine. Yeah.
Wait, so what would Levin say? Like both or?
That I'm not sure on that one.
Oh,
I have to see. Yeah, I'm not sure.
Okay.
Yeah. Right.
Okay.
And then you're gonna see, like, when you do these reactions, you're gonna see like 1-2 addition, 1-4 addition, right? Where what that basically means is that this is the first bromine you added on right here, right? And I'm gonna do that in red. If you count how many carbons it takes to get to the other bromine, that's 1-2. So that's 1-2 addition, right? This is the first bromine that you added on. If you count how many,
1, 2, 3, 4.
Yep, that's 1-4 addition, right? 1-2 addition, 1-4 addition.
So 1-2 is kinetic.
1-2 product, 1-4
or
product.
Thermo? Yeah.
So I don't like to think about it like that because there's exceptions for the examples.
Okay.
Yeah, but usually, typically, 1-2 is kinetic, 1-4 is thermodynamic, but not all the time. So I don't.
Not all the time.
That's why I don't like teaching it that way. But I'm just showing it to you just in case you see it on lecture.
Okay.
1-2, 1-4. Right. Okay. So I'm not gonna update the step-by-step procedure yet. I'm gonna wait until I get like your lecture notes from Levin's.
Yeah.
And then update this just for Levin's class.
Yeah.
Right.
Cool.
Okay. Now I'm gonna give you a practice problem with the X2.
Okay.
Okay. Wait, let me see. Notes here.
Oh.
Ooh, yeah.
Wait, can you go to the problem? I just want.
Yeah. Oh yeah. I didn't.
Oh, you didn't write it yet. Sorry, I went to the restroom.
Yeah, it's okay. It's okay. Okay, let's do this one. Oh yeah, and then most likely you see this with like CCl4, a product solvent, so there's no competition of nucleophile like water or alcohol.
Okay.
Right. And let's do for Levin's -78 degrees Celsius and 40 degrees Celsius. The two scenarios there. Okay, try that.
Okay.
Okay. Okay. Hey Sufarna, were you able to get the?
Yeah, I didn't send it to you. Do you want me to?
Yeah, you can send it to me, or you can describe to me how you what your thought process was. Like how would you approach this problem, and I could like
Yeah.
it.
Okay, so I found the nucleophile, like the carbon that connects to MGBR, sorry. And then I identified the electrophile, which is the double, like the carbon on the carbonyl.
Yep. Right.
Then I made the nucleophile attack the electrophile, and then I pushed up the bond. I pushed up the electrons. Yeah, there you go.
Right.
And then I did my arrow, and then I drew it out, and then I used H3O to make it a water, and then
did you draw out like this? Because this is the part where some people add an extra carbon by accident or lose a carbon by accident. Like, did you add an extra carbon or did you draw exactly like this?
Wait, my drawing's a little funky because wait.
Did you draw it like this?
I'm just gonna send it to you.
Okay. Does it look like this? More like this?
I think it looks the same.
Wait, hold on. What the heck is that? Like this.
No.
No. Let's see.
Wait.
Let me see your thing here.
Discord's being weird. I think it's the same. I just drew it in different orientation, I think.
Yeah. Let me see. Did you send it on? Oh, I see. Yeah, Discord. Yeah. Discord. See. Butyl, ethyl, O minus, and yeah, it's the exact same thing. Nice,
Okay.
nice.
I
And
did
then,
I did it right?
yeah, you did it right. You did it
Okay.
right.
Okay,
Correct.
cool. Okay.
Nice. Okay. Right. So that's organometallic reaction review.
Is there a reagent that like would result in no reaction? Like if it wasn't H3O plus or if it wasn't something with a positive
Yeah.
H, would there be?
If you were to have an alkene molecule and you try to react that alkene with an organometallic, this time let's use organolithium, Li, second step H3O plus, this would be no reaction. Because this carbon here directly attached to the Li is the nucleophile. There's no electrophile here in this molecule. When you see an alkene, think of the alkene as a nucleophile and base. Right? Where like both carbons give it a nucleophile base, nucleophiles will not interact with each other. They will not react with each other. But nucleophiles would attack an electrophile if there was an electrophile here. But since there's no electrophile here, that's no reaction, NR. But for helix class, you don't have to worry about that. Like I think you think of NR because Levens had NR problems, right, on her quizzes.
Oh yeah, she had a lot.
Yeah, helix does not do that to you guys. So.
Oh really?
Yeah, he doesn't do that. He doesn't do that.
Oh, that's so sweet. Okay.
Yeah. So you don't have to worry about NR reactions. Yeah.
Okay. Amazing.
That's good. That's good.
Yeah, Levin's always tried to like mess with us.
Yeah, I know. Wiley has to go through that this quarter with his class with Levin.
Oh, I'm
I
With
hate
so
NR.
sorry.
Yeah.
I hate her vocab too. Oh my
Yeah.
God,
I'll
it's so
have 38
annoying.
points.
38 points. I know, it's so
Something like
much. She loves her vocabs. And her hand-drawn spectroscopy too, like the HNMR, IR.
Oh, I didn't
Those
see
are not that
spectroscopy on
bad.
my practice quizzes she sent out. So
Yeah,
I think we're
but
good.
it's actually like pretty like useful how she hand draws it, because sometimes when they print it out, like it sometimes emerges and it's very funky, so it's not as clear. But when she hand draws it, like it's very clear on what she wants you to know.
Yeah.
Okay, so let's talk about reducing agents with aldehydes and ketones. Let's just say we have this ketone here. It works the exact same way as an aldehyde. The two reducing agents that you're gonna see is LiAlH4 or NABH4. Right, second step is gonna be acid workup. What that's gonna do is that's gonna convert the carbonyl into an alcohol. And you don't have to know the mechanism for that. You're not gonna be tested on the mechanism for that, right? But this is reduction here, right? Because we're reducing this carbonyl into this alcohol. Reducing meaning that we're gonna remove a bond to an electronegative atom, right? This carbonyl carbon here had 2 bonds to the oxygen, but when we reduced it, we took away that 1 bond to oxygen, right? Another way you can look at it is gaining a bond to hydrogen. That's reduction, right? Before, this carbon here had 0 bonds to hydrogen, but when we reduced it, we gave it 1 bond to hydrogen right there, that invisible hydrogen right there, right? Because we're trading 1 bond of an electronegative atom to a bond with a hydrogen right there. That's reduction, right? Oxidation is is different, right? If this is a secondary alcohol, you could, and you do need to know this for synthesis. If you want to go for an alcohol to a carbonyl, you gotta oxidize it using PCC or Jones from a secondary alcohol. Right. Let me actually just give you primary alcohol as well, because it would matter what you do. Right. Now, let's say we had an aldehyde instead of a ketone. Same reagents to reduce it. LiAlH4 or NaBH4. That would reduce that carbonyl into an alcohol. But I'm gonna draw the alcohol out like this, right? Because this carbon here had this hydrogen. That hydrogen is still there. But it also has another hydrogen because we got rid of a bond to oxygen and traded it with the hydrogen right there. This OH here is this carbonyl here, but I just flipped it downward because like it looks nicer this way, if that makes sense.
Yeah.
Right, now, if we want to get to the aldehyde, we want to use a specific oxidizing agent. Do you remember what that specific one is? Like, is it PCC or Jones?
I think it's Jones.
Jones would give you something else. Something else, right? Jones is a stronger
Oh, is
oxidizing
Jones
agent.
only for secondary and tertiary?
Tertiary will give you no reaction for tertiary alcohol. Right, and I'll show you why. So think of Jones as a strong oxidizing agent, right? And PCC as the weak oxidizing agent. We want to use PCC here if we want to convert a primary alcohol into an aldehyde, because we only want to, you know how this second primary alcohol has two hydrogens right now? We only want to trade one hydrogen to one bond to oxygen, right? We don't want to overdo it. We don't want to trade both. If we want to trade both, we got to use a stronger oxidizing agent, which is Jones. And that's going to give us the carboxylic acid. Right? And this is one of the reactions you need to know, because this carboxylic acid here is unit 1 of 118C. Right?
Oh, I see.
Because if you were to track this carbon here of the alcohol, if you use a strong oxidizing agent, this carbon here, like if we will get rid of the two hydrogens and substitute it with two bonds to oxygen like that. Like that.
Do I have to know the mechanism for this?
No. You don't have to know the mechanism for this. You just have,
really?
have to recognize the reagents. Yeah. Don't need to know the mechanism for this. Yeah. Don't worry about it.
Oh wow, Helix is so nice.
Yeah. Well, this one's here, like you're not tested on the mechanism like in general for like all 118 ABC.
Were we not?
No,
Oh,
yeah,
I just
yeah,
remember
yeah.
knowing the mechanism for like everything because I was so scared somebody was gonna ask.
Yeah. For 118B, leavers, there was a lot of mechanisms, like with alkene reactions, alkyne reactions, aldol, Robertson
Yeah.
annihilation. Yeah. That was when you saw a lot of mechanisms. But don't worry, you will need to know a lot of mechanisms when we get to the new material.
Oh, lovely.
Yeah. Right. Okay. Now, the reason why secondary alcohol does not matter is because we only have one hydrogen to substitute, right? And then we can only get to here, to that carbonyl. So that's why we can use PCC or Jones. If we had a tertiary alcohol like this, and we try to PCC or Jones it, like oxidize it, NR. Because
because there's no available hydrogens.
right,
Okay,
there's no
got it.
available hydrogens for us to substitute it with. Yeah. Right. So that's like what I want you to think about, and moving forward, like think about the reason why like the reaction goes, and if it doesn't go, right? Like what you said, this tertiary alcohol here had no available hydrogen to substitute or oxidize with, so that's why it's NR. Don't just like try to memorize it, don't try to understand.
Yeah, I've
why.
learned that in 118A that it doesn't get you very far.
Yeah, it doesn't get you very far, right? Because a lot of reactions they build up, they stack up on each other. You're gonna get overwhelmed when you try to stick with that same strategy. But don't worry, because you could categorize them in the same mechanism. The same mechanism can give you a lot of reactions. But if you know that one mechanism very well, you could do like the lot of reactions clearly while understanding it.
Okay.
Yeah. Okay. So that was organometallic reagent and hydride reagents. The other ones will get more deep into the new material. So that's what we're gonna go over in tomorrow's office hours.
Okay, perfect.
Yeah. Nice. Okay, so now I'm gonna just give you 2 practice problems, Suparna, to end off the office hours, and I'm gonna check Wiley's answer after that. Right. Okay. And I'm gonna give it into you in a different order here, different format here. Try that. And try. This. Just these two, and then we'll be done for today.
Okay.
Okay. Let me see your work, Wiley. Okay. So this first one here, you reacted with that. Okay. Oh, your work has two fused six-membered rings, but one ring is six-membered, the other ring is five-membered.
Oh, you drew. Wait.
Five-membered, yeah. Yeah, but it's okay. It's okay. I think the process will still be the same. Like the left one is a six-membered ring. The right is the
I didn't
five-membered
even
ring.
notice.
It's okay. It's okay. I think
Whoops.
the concept will still be the same though. Like
Okay.
I don't think it'll change. It's carbocated right there. Okay, tertiary lilac, boom. Shift that there, secondary lilac. Okay, that's that resonance set. Let's look at the other one. Boom. Okay, shift that over there. Boom. Okay. Yep. X that out. Ignore that one entirely. Check mark that one. Keep that one. Tertiary lilac. That's the kinetic one. Yes. Alkene is right there. Thermodynamic. That is the more stable alkene, which is this 1, 2, 3 tri-substituted one. Yeah, you got it right. Yeah.
Okay.
Yeah. Nice.
Now I can see the 1, 2, and 1, 4 when I count.
Right.
1, 2, 3, 4. Yeah.
And which one would be 1, 2? Which one would be 1, 4?
Kinetics 1, 2.
Yes.
1, 4.
In this example.
Yeah, example. Yeah.
Yeah, not all examples would be like that. Right. That's good. Nice job. Okay. Suparna? Oh, I know it's fast. It was fast. But then, do you have a answer for these here?
Yeah, I finished 2. I'm still working on 1.
Okay. What would 2 look like?
Just replace the carbonyl with a alcohol.
Yes. Right. Okay.
Okay, wait. Is 1 no reaction?
1, there will be a reaction.
Okay.
There will be a reaction.
I don't know what it is.
So this first reagent here is an organometallic organolithium, because you see the Li right there. Think of that as MgBr. When you see Li, whenever you see Li, think of that as MgBr.
Oh, okay.
Right. This is the nucleophile. This is the electrophile. Now try predicting the product. I just reversed it, right? The reactant is now the organometallic. The reagent is now the carbonyl. Right. But they will still do the same thing. It means the same thing still. Like they're both reacting with each other. It's like A plus B is like C, but different order. You know, it's like saying B plus A is C now.
Can I just explain it to you, or?
Yeah.
Okay, so the nucleophile is going to attack the electrophile, and then it's going to push up those electrons, and then you're going to form a new bond between that star and dot.
Right. Okay.
Oh, and then H3O is going to, the carbonyl is going to turn into an alcohol.
Yes, you got it, like that, right? And you got this as the product. No extra carbon, no missing carbon.
Wait, I'm checking right now.
Yeah.
Yeah.
Okay. Yeah. That's good. Nice. Okay. So that was like most of the well, actually, yeah, like 118A review. Tomorrow we'll do 118B review and get into the new material tomorrow. Yeah.
Okay, perfect.
Yes.
Thank you so much.
Of course.
Cool.
Have a nice night, guys.
See ya.
See ya.
You too. Thank you so much.